My name is Rishabh and I'm going to talk about the topic effects of hardness of water of subject engineering chemistry. I am from CSE AAML department. What is hard water? Hard water is a water that contains high concentration of dissolved minerals, primarily calcium Ca2 plus and magnesium Mg2 plus ions. These minerals dissolve naturally as water moves through and over rock formation such as limestone, chalk, gypsum and dolomite over a long period of time. The process is entirely natural and occurs as a part of hydrological cycle where rainwater, which is slightly acidic due to dissolved carbon dioxide, gradually dissolves minerals from the earth crust. Unlike soft water, hard water does not lather easily with soap and tends to leave behind chalky white material mineral residues on surfaces it comes in contact with. It is one of the most widespread and common water quality issues faced globally, affecting both urban and rural population across every continent. Types of water hardness. Water hardness is broadly classified into two distinct types based on the chemical nature of the dissolved minerals. Temporary hardness and permanent hardness. Temporary hardness is primarily caused by dissolved bicarbonates of calcium and magnesium in water. This type of hardness is relatively easy to address and can be removed simply by boiling the water, which causes the bicarbonates to decompose into insoluble carbonates that precipitate out as a white deposit. Permanent hardness, on the other hand, is caused by the presence of sulfates, chlorides, and nitrates of calcium and magnesium dissolved in the water. These compounds are thermally stable and cannot be eliminated through boiling alone, requiring more advanced treatment methods such as chemical softening, ion exchange, or reverse osmosis. In many regions, water sources exhibit a combination of both types, making treatment more complex and layered. Understanding which type of hardness present in a water supply is critical important for selecting the most effective. How hardness is measured? Water hardness is measured and expressed in several units depending on the country and context of use. The most universal accepted unit is milligrams per liter or its equivalent parts per million expressed as calcium carbonate CaCO3 equivalent. In some European countries, hardness is measured in degree of hardness, while French degrees and English degrees are also used in specific regions. According to the standard classification, water with hardness level below 60 mg by liter is considered soft. Water between 60 and 120 milligrams per liter is classified as moderately hard, and water between 120 to 180 milligrams per liter is classified as hard, and water exceeding 180 milligrams per liter is classified as very hard. The measurement of the hardness is typically carried out with laboratories using titration method with EDTA, which reacts especially with calcium and magnesium ions, giving an accurate reading. Modern digital testing kits and test strips are also widely available for quick field assessment. Accurate hardness measurement is essential not only for domestic purpose but also for ensuring that industrial process, boiler operation, food manufacturing and water treatment plants function safely and efficiently within prescribed limits. Effects on soap and detergent efficiency. One of the most immediate, noticeable, and practical inconvenient effect of hard water in everyday life is the significant reduction in lathering and cleaning efficiency of soap and detergent. Calcium and magnesium ions present in hard water readily reacts with the fatty acid salts, the active cleaning agents found in soaps to form insoluble compounds collectively known as soap scum or lime soap. This compound appears as a white, sticky or waxy residue that clings to the surface, including bathroom tiles, bathtub skin, glassware, and clothing. Because a large portion of the soap is consumed in this reaction, rather than performing its intended cleaning function, considerably more soap or detergent must be used to achieve the same level of cleanliness that a soap water would provide with a smaller quantity. This results in a direct and measurable increase in the household expenditures on cleaning products over time. The soap scum deposited on fabrics during laundry does not rinse out easily, causing clothes to feel rough, appear dull, and faster with a repeated washing. Hard water and human health. The relation between the drinking hard water and human health is multifaceted and has been the subject of extensive epidemiologically and clinical research over several decades. On the positive side, the calcium and magnesium naturally present in hard water contributes to daily dietary intake of these essential minerals. Calcium is critical for bone density, nerve function, and muscle contraction, while magnesium plays a key role over 300 enzymatic reactions in the body, includes energy production and protein synthesis. Several studies have found a statistically significant inverse relationship between the water hardness and the incidence of the cardiovascular disease, suggesting that the population consuming hard water may have lower rates of heart attack and strokes. The World Health Organization has acknowledged these potential benefits and has considered setting minimum recommendation levels of calcium and magnesium in drinking water. However, the picture is not entirely positive. Individuals who are genetically predisposed to kidney stones formation face an elevated risk when consuming water with a very high calcium content, as excess calcium can combine with oxalate or phosphate in urinary tract to form crystals and stones. Long-term consumption of extremely hard water has also been tentatively linked to gallstone formation and certain joint condition in some studies. Though the evidence remains inconclusive, health authorities generally recommended that people living in a very hard water areas have their water tested and consider appropriate filtration for drinking water and cooking purpose, while still being mindful of the potential cardiovascular benefits of moderate mineral intake. Effects on the textile industry. The textile and fabric manufacturing industries is heavily dependent on water at virtually every stage of production, from fiber preparation and dyeing through to finishing and washing, making it one of the most industrial sector most seriously affected by water hardness. Calcium and magnesium ions in hard water interfere with the chemical processes involved in dyeing by competing with the dye molecules for fiber bonding sites, leading to uneven dye uptake, patchy color distribution, and duller, less vibrant shades in a finished fabric. The mineral ions can also react directly with certain synthetic and natural dyes to form insoluble compounds, resulting in color precipitation and loss of dye efficiency, which in turn increases the cost per unit of dye required. Industrial and boiler scale problems. In industrial settings, the effects of hard water reach their most economically significant and potentially dangerous expression in operation of steam boilers, heat exchangers, cooling towers, and other thermal processing equipments. When hard water is repeatedly heated in a boiler, the dissolved calcium and magnesium carbonates decompose and precipitate to form a dense rock-like scale on the internal metal surface of the boiler, particularly on heat transfer surfaces such as fire tubes, water tubes, and heating coils. Boiler scale has an extremely low thermal conductivity, roughly 30 to 40 times lower than that of a steel, meaning that even thin layer of a scale acts as a powerful insulator, preventing heat from being efficiently transferred from combustion gases to water inside the boiler. To maintain the required steam output, the boiler must burn additional fuel, significantly increasing energy consumption and optional cost. The scale layer thickness, the outer surface of a boiler wall unable to dispatch heat properly, reaches dangerous elevated temperature. This overloading causes the metal to undergo physical changes including wrapping, cracking, and tinning, which leads to the failure of the tube. Scale in industrial boilers, heat exchangers, and cooling system, combined with the cost of water treatment chemicals, descaling operation, maintenance shutdown, this thermal overloading causes the metal to undergo physical changes including wrapping, tinning, cracking, which can ultimately lead to tube failures, boiler explosion, and catastrophic industrial accident. Beyond the safety risk, the economic impact of boiler descaling, unplanned and maintenance shutdown, and equipment's replacement is enormous. Industrial estimates suggest that hard water related scaling costs power plants, chemical manufacturers, food processors, and other heavy industrial billions of dollars annually in wasted fuel and maintenance expenses worldwide. Comprehensive water treatment program, including chemical scale inhibitors, ion exchange softening, and regular blowdown producers are standard practice in any modern industrial facility operating with steam boilers. Effects on agriculture irrigation. Agriculture is one of the largest consumer of fresh water globally, and quality of irrigation water, includes its hardness, has direct and long-term consequence for soil health, crop productivity and sustainability of farming operation. When a hard water is used for irrigation over extended periods, the repeated application of calcium and magnesium rich water causes these minerals to accumulate in the upper layers of the soil. Over time, this leads to a condition known as a soil crusting, when a hard, compacted surface layer forms that imitates the infiltration of water and air into the soil, reducing the effectiveness of irrigation and hindering root development. The accumulation of calcium carbonate in the soil progressively raise soil pH, shifting it towards alkalinity in hard water and corrosion. While the most virtually obvious and common discussed effect of hard water is build-up of a lime scale and a mineral deposit, hard water can paradoxically also contribute to certain forms of corrosion in plumbing system and industrial equipments. Through the relationship between the hardness and the corrosion is more and context dependent than that of a soft water. In some plumbing configuration, particularly those involving two different types of metals in contact with each other, such as copper pipe joined to galvanized steel fittings, hard water with its relatively high electrical conductivity due to dissolved mineral ions can act as an effective electrolyte and facilitate galvanic corrosion. In galvanic corrosion, one metal acts as an anode and corrodes preferentially. Economic cost of hard water. The economic impact of a water hardness is vast and pervasive, extending from individual household budget all the way up to the national infrastructure cost and industrial profit margin. At the household levels, families living in hard water areas consistently spend more on soap, shampoo, and cleaning products and laundry detergent compared to those in soft water regions, simply because of the larger quantities are required to achieve equivalent cleaning results due to reduced efficiency of surfactants in mineral-rich water. Energy bills are also higher, as scale insulated water heaters, boiler, and appliances consume substantially more electrical or gas to perform same heating task. The need for more frequent appliances, repairs, and earlier replacement of water using equipments add further financial strain. A comprehensive study conducted in United States estimated that a typical household using untreated hard water spends several $100s more per year on energy and cleaning products compared to an equivalent household using a softened water, and this figure does not account for appliances replacement cost. Methods to treat hard water. Given the wide-ranging negative effects of hard water across domestic, industrial, and agriculture contexts, a variety of treatment methods have been developed to reduce or eliminate water hardness, each with its own advantages, limitation, and applicability depending on the specific use case and the degree of hardness involved. Ion exchange water softening is the most widely used residential and commercial method, employing a resin bed containing sodium ions that are exchanged for the calcium and magnesium ions as water passes through, producing softened water that is far more compatible with soap and appliances. The resin is periodically regenerated using a concentrated salt solution which restores its ion exchange capacity but produces a brine waste stream that requires responsible disposal. Reverse osmosis is a highly effective treatment method that forces water through a semi-permeable membrane under a pressure, removing not only hardness minerals but also a wide range of other dissolved contaminants, including heavy metals, nitrates, and organic compounds. RO produce very pure water ideal for drinking and cooking but generates a concentrated reject stream and operates at relatively low flow rates, making it better suited for point of use application than whole house treatment. Lime soda softening is a chemical treatment method widely used at a municipal and industrial scale where lime and soda ash are added to water to precipitate the calcium and magnesium as insoluble carbonates and hydroxides, which are then removed by sedimentation and filtration. Boiling remains a practical method for removing temporary hardness in a small volume of water. through it is an energy insensitive and ineffective against permanent hardness. Chelating agents and scale inhibitors, chemical compounds that bind to calcium and magnesium ions and prevent them from precipitating onto surfaces, are used industrial to control scale formation without physically removing the hardness minerals. Electronic and magnetic water conditions are marketed as a maintenance-free, chemical-free alternatives that alter the behavior of mineral ions through magnetic or electric fields. Through the scientific evidence for their effectiveness remains limited and concise. Distillation produces extremely pure hardness free water but is energy insensitive and generally impractical for large scale application. The choice of the treatment method depends on carefully on the assignment of the water hardness level, flow state requirement and budget constraint. Conclusion and key takeaways. The hardness of water is a pervasive and multidimensional issue whose effects ripple across virtually every aspect of human life and industrial activities. As explored across the preceding slides, the consequences of hard water range from the minor inconvenience of poor soap lathering and dull hair to the serious and costly problems of industrial boiler failures, reduced agricultural productivity, compromised public health, and significant environmental pollution. The economic toll of the hard water is enormous, costing households, industries, and government collectively hundreds of billions of dollars annually in wasted energy, excessive chemical use, and appliances replacements. Infrastructure maintenance and water treatment. Despite these many challenges, it is important to recognize that hard water is not universal harmful. The calcium and magnesium it contains contributes positively to the human nutrition and may offer cardiovascular protective benefits, underscoring the need for a balanced approach to a water quality management rather than a blanket condemnation. The critical takeaway is the awareness in the first and most essential step towards addressing the problem effectively, industrial and business. And policymakers must invest in understanding the hardness level of their local water supply through regular testing and monitoring, and then select appropriate treatment and management strategy that are tailored to their specific needs, scale of operation and environmental context. Advantages in water treatment technology continue to offer increasingly efficient, cost-effective and environmental sustainable solution for managing water hardness. Education infrastructure, investment and proactive water quality governance are the pillars upon which a future with a better water management must be built, ensuring that water, the most essential of all the natural resources, is used safely, efficiently, and sustainably by all. Thank you.